Hello once again, thanks for joining us. This is the Space Nuts podcast. My name is Andrew Dunkley, your host, and with me, as always, is astronomer at large, Professor Fred Watson. Hello, Fred.
Hi, Andrew. Very good to be here. I'm always glad to see your smiling face when we kick off with a Space Nuts recording.
Thank you, sir, and congratulations, episode 250.
Who would have thought it?
When we started, I did not know if this venture would turn into anything, and I'm just so stunned and humbled by the global support that we get. It's been a real joy to connect with so many people, not only via the podcast but via social media, and to be able to swap messages and jokes and just learn a little bit about the people who love astronomy so much. And it's a thrill, and of course we're not stopping now. It makes it sound like we've come to the end, but we haven't. No, we'll keep on keeping on.
What are we going to do when we
episode,
get to 1,000, though? When we get to episode 1,000 or 500?
Well, I think by then they'll probably be digging us up to see if we want to do any more.
Speak for yourself. I'm hale and hearty.
Oh, dear. Yes.
I've just spent a lot of money on my teeth and my knee. I want to get good value for it.
Oh, dear. And I just built a putting green, and I intend to use that for at least 30 more years.
Yeah, absolutely.
What a waste of money if it's just to sit there and look forlorn. Today we will be answering audience questions. That was the original plan, and we've got questions from Cassandra, Ryan, Graham, Paddy and Alyssa, Ralph, Andrew and Mark about all sorts of subjects, but we had one interesting combo question from two different people who don't know each other, but they're both sort of asking the same thing. So we're going to do that as a single double question. Don't ask me how, but we'll play them both at once so that they're talking over each other. Actually, I can do that. But anyway, we'll do that. But first, Fred, some very, very sad news. And that is the death of Apollo 11 astronaut Michael Collins. I heard the news this morning that he'd passed away at the age of 90 after a battle with cancer. And look, he was part of the reason I got so interested in space and astronomy and space travel. I was inspired to go to NASA. As soon as I saw Apollo 11, I always thought, I'm going to go there and see this place and learn more about it. And I think my favourite moment was going to the Saturn V display at NASA in Florida and seeing that Saturn V rocket hanging from the ceiling in its various stages. It was mind-blowing. And, Michael Collins was a part of the reason that happened, because and he's probably part of the reason this podcast is happening, because he was just one of those people that was etched into my mind from a very young age. I saw the Apollo mission at the age of 7. I think you were probably 47, 57 at the time.
Something like that, yeah.
Yeah, and yep. He was a follower of the Space Nuts podcast. I don't know if you or many people know that. I didn't make a big deal of it, but he liked some of our episodes over the last couple of years.
Seriously?
I thought that was... Yes, indeed.
I didn't know
I was stunned and amazed that he'd paid us any attention at all. So, what a great bloke.
Yeah.
What a great bloke.
Yeah.
And... it's sad, but he lived a long and happy life. And if I could, I'll just read a statement from his family.
Yep.
They say, "We regret to share that our beloved father and grandfather passed away today after a valiant battle with cancer. He spent his final days peacefully with his family by his side. Mike always faced the challenges of life with grace and humility, and faced this, his final challenge, in the same way. We will miss him terribly, yet we also know how lucky Mike felt to have lived the life he did. We will honour his wish for us to celebrate, not mourn, that life. Please join us in fondly and joyfully remembering his sharp wit, his quiet sense of purpose and his wise perspective gained both from looking back at Earth from the vantage of space and gazing across the calm waters from the deck of his fishing boat." That's a statement from his family, and I think that's lovely, and I think it's a perfect way to see him out from his mortal coil. And I never got to meet him. I did meet Buzz Aldrin, and Buzz, of course, the last of the trio that went to the moon, and that most famous journey of Apollo 11. Yeah, what a great bloke.
Indeed. And just a footnote to that, I was listening this morning to a recording of him. He was giving us a bit of a speech 2 years ago, so it would have been 88. And you would have thought it was a man 40 years younger. He was firing on all cylinders, very, very, very calm, and it was just the same voice that he had when he was in the command module of Apollo 11. Quite remarkable.
One of my favourite stories about Michael Collins, and this is just a bit of trivia that not too many people would be aware of, although I think I have mentioned it once during our time during this podcast. He took a photograph from the module as he orbited the moon while Neil Armstrong and Edwin Aldrin were on the surface. And the photo consisted of the moon in the foreground and the Earth in the background. And at that time, it was the only photograph in history where he was the only human being not in the photo. And, that's pretty extraordinary when you think about it. Yeah. He took the photo of everybody else that existed in the world at the time, except for him. That amazed me.
Yeah,
it's a piece of trivia, but
it is. It's remarkable.
It's pretty special.
Yeah.
Okay. We will long remember him, of course. Let us move on to our questions. We've got 2 questions. I might just play them back to back, and then we can answer them both together, because they both kind of walk the same path in very different ways. These are questions from Cassandra and Ryan. So let's see what they're quizzing us about.
Hey y'all, my name's Cassandra and I am from Tennessee. It's in the United States if you're not familiar with the states. And I just have a really simple and weird question for y'all. Before I ask y'all, I do want to put forth that I am a social studies teacher, so science is not my forte, but I do love learning about space. I'm very interested in space, and I love hearing how you guys take advanced space terms and make them accessible to everyone. So my question was originally put forth by my boyfriend, who is a major space nut, and he's always asking questions that make my brain want to explode. That's what I love about him. But he always asks me, if there was a car in space traveling at the speed of light, so assuming a car could survive in space and travel at the speed of light, and it turned on its headlights, would you be able to see the headlights? Let me know what y'all think about that.
That is a really good question. I've heard that before. And Cassandra, there is such a car. It's a Tesla. But before we answer the question, we'll go to Ryan, because he asks something not dissimilar.
G'day guys, love your show. Ryan here from Australia. I just want to ask a simple question, if there is such a thing. If you had 2 very fast rocket ships end to end in the vacuum of space, and they both accelerated away from each other at the speed of light, but the passengers, well strapped in of course, looking back, would they be seeing twice the speed of light? I know it's a crazy question, but I've often thought about it. So, yeah, interesting. Let us know. Cheers.
Thank you, Ryan, and thank you, Cassandra. And speed of light questions are always intriguing, and I don't know which way you want to go first, but let's sort of go, okay, a car in space travelling at the speed of light, you turn the lights on. What happens then?
So the thing that connects these 2 questions, Andrew, and they're great questions, and they're the sort of thing that people do think about. What connects them is that you're adding velocities. So with the car headlights, the car's going at, it can't travel at the speed of light because only light can do that, but it can be very, very near the speed of light because we do that with subatomic particles. So it's travelling almost at the speed of light, turns on its headlights. The light from the headlights is travelling at the speed of light. So you think, that to a stationary observer, the beam from the headlights must be travelling at almost twice the speed of light. And Ryan's question is the opposite. If you've got 2 things going away from each other, what is the speed at which they're separating? Is it twice the speed of light if these two rockets are going at almost the speed of light? And the answer is no. And that's because when you get into relativity, and relativity tells us all kinds of very strange things, velocities or speeds don't just add the way we do in the normal world. I'm very reluctant to put formulae into this podcast, but it is actually a relatively simple one. So I'm going to throw it in anyway.
You're pushing the
limits. I know.
Of adequacy, Fred.
Well, I can do it without it. I mean, basically, you never. The answer is always less than the speed of light. That's what happens.
Right.
So two rockets approaching each other. You expect their closing speed to be twice the speed of light if they're approaching each other, and that works in the world where they're not going anywhere near the speed of light, normal cars. But when you get to these very high speeds, relativity becomes more and more dominant, and what happens is the addition is not just a simple addition. It's not just one velocity plus the other. It's actually one velocity plus the other divided by 1 plus the two velocities multiplied together divided by the speed of light squared. That's the formula. Don't worry about it.
I've got a headache.
But what it tells you is that, supposing they're both travelling together, closing at 0.9 of the speed of light, if they're coming towards each other, it works the same the other direction. Their closing speed is actually... Each one's going at 0.9 the speed of light. They're approaching. You'd expect it to be 1.8 times the speed of light, their closing speed, but it's not. It's 0.99 times the speed of light. It's much closer. If people are interested in this and interested to see the formulae, there are one or two sites on the interweb. Just check out relativistic velocity addition, and it'll tell you all you want to know, probably more besides.
Yeah,
because I'll
remember that.
Yeah, a lot of it goes into reference frames and things like that we don't want to worry about. But the bottom line is that velocities don't add in the normal way, and there's a practical demonstration of this. We know it happens. We know it works because, as you well know, the two beams of the Large Hadron Collider, which are spinning round between France and Switzerland in opposite directions at very nearly the speed of light. I think it's 0.99995% of the speed of times the speed of light. So they're effectively travelling at the speed of light. They collide them, and the collision speeds are that, an increased fraction of the speed of light, but it doesn't exceed it. So it works.
Okay. Yeah, it does. Yeah. So what you're actually saying is that we should change the speed limits of cars to near the speed of light, and we'll be much safer.
Yeah, well, that's right, because you can never go over. It's like the speed limiter on a truck. It's the same sort of
you can't exceed it.
It works in physics. You can't exceed it.
Yeah. Wow. All right. It's a question I've heard many times, and one that puzzles people. And yes, you'd think if you're travelling near the speed of light and you turn the lights on, that must do something, but it doesn't do anything much. So
the answer is yes, you'd see the headlights. It actually depends on where you were. Clearly, if you were behind it, you wouldn't. For an observer, a stationary observer, if I can put it that way, you'd see the headlights because the light will be coming to you at the speed of light.
And if we were driving towards each other at 100 kilometres an hour each, our closing speed would be 200, all going apart, same effect.
Yeah.
But at the speed of light or near speed of light, it's cancelled out.
It's not the case. Well,
you've reached the limit.
It gets progressively slower as you get nearer. The closing velocity gets progressively... It just gets nearer and nearer to the speed of light as the two individual things approach it, but it never exceeds it.
There you go, Cassandra and Ryan. You have your answer, and Cassandra, good luck explaining that to your boyfriend.
What a way to start a Thursday morning, Andrew, with
yes, indeed.
relativistic physics.
Exactly right.
Sorry about that.
No, that's okay. Let's move on to our next question, and this one comes from Graham.
Hello, Andrew and Fred. My name is Graham Murray, and I'm calling from Saltburn by the Sea up on the northeast coast of Yorkshire, England. Saltburn is only 10 miles from Marton, where Captain Cook was born, and a little over 7 miles from Staithes, from where Captain Cook sailed on his voyage that discovered Australia. So in this part of the world, we're very proud of our historic attachment to Oz, and like many, I have family and friends on both coasts down there. Please could I ask you to talk about the moon, specifically the phenomenon of tidal friction? What is the link between water on the Earth and lunar friction, and why only water and not, say, magma beneath the crust? I'm finding online explanations difficult to comprehend, so I'm wondering if your tried and tested communication skills will make this easier for me. I believe on one of the Apollo missions, a parabolic dish was placed on the lunar surface, and that lasers on Earth can be fired at it, reflected back, enabling precise measurement of the distance between the spheres. This has proven that the moon is gradually becoming ever more distant from us. Apparently, back in the age of the dinosaurs, the moon would have appeared considerably larger in the sky. I'm also of the belief, rightly or wrongly, that the presence of the moon stabilizes the Earth's rotation. If this is correct, what are the implications if the moon is becoming increasingly distant? Since discovering Space Nuts, I'm working through the back catalogue. Love everything you're doing and never miss any output, whether on podcast or YouTube. Thanks, guys, if you can help explain it all.
Wonderful, thank you, Graham. And based on your question, Fred is now going to write his next book in 75 volumes to answer everything you've asked. Before we get to that, though, Graham mentioned Captain Cook, who came from that particular part of the world.
Yep.
And yesterday actually was the anniversary, the 28th of April, of his setting foot in what he named Botany Bay. And Botany Bay is in Sydney Harbour. They tried Sydney Harbour and went, ew. And, or was it the other way around? Captain Phillip.
It was the other way around, Andrew.
Bay. Yeah. Captain Phillip went into Botany Bay after it was discovered by Captain Cook and
yes, that's
went,
right.
ew. And then went back out and went into Sydney Harbour and went, oh, this is nice. We'll stay here. What and all. But Captain Cook, the anniversary yesterday of his discovery and setting foot in Botany Bay, he originally named it Stingray Bay for obvious reasons, because it was full of stingrays. But after Joseph Banks went for a wander and went, oi, what's all this here then? Which is exactly how he sounds. He brought back all these botanical bits and pieces, and they went, wow, this is pretty cool. We'll call it Botany Bay. Because they found all those amazing plants, including one that's called the Banksia, named after Joseph Banks, of course. So just a little bit of a connection between where Graham is from and why we are here in Australia at the moment. Lunar friction.
There's more to it than that.
Oh, is there?
Well, there's a connection. I know that area very well.
Of course. Oh, yeah. I was going to mention that too, but I totally forgot.
But there is another point that we're always at pains to make here in Australia. And forgive me, Graham, for mentioning this, but Captain Cook did not discover Australia. A lot of people knew about it already.
I wasn't going to split hairs.
No, it's not splitting hairs, really, if you're one of the indigenous people who lived, whose ancestors have been here for tens of thousands of years. So it's a matter of, I suppose, communities coming together rather than discovery, something like that.
Yeah, and if you really do want to split hairs, which I'm going to do now, the first Europeans to discover Australia were actually, was it the Portuguese or the Dutch?
It's the Dutch, yeah.
It was the Dutch, yes. I thought so. That explains my wife. She's Dutch.
Yes.
But yes... a lot of people found it, and in fact, here's another piece of trivia. When the first fleet arrived, we'll get there eventually.
Yeah.
When the first fleet arrived in 1788, there were 2 French warships off the coast.
Yes, there you go.
They were here going, "Oi, this is ours. You leave." Terrible French accent. I think it turned into Spanish somewhere along the way. They might have been here too. Now, lunar friction.
So, I've forgotten the question. No, I haven't. It's okay. Look, Graham, the main thing is, and you kind of put your finger on it in your question, why only water? Well, and why not say magma beneath the crust? And it's everything. The tides actually pull everything around. So the surface of the Earth moves twice a day by something like a foot on average. It varies from place to place. So it's not just the tides going up and down. We are going up and down as well.
That's why I miss those crucial putts. It's the movement. It's tidal friction. That's what it is.
That's right. The ground's changing under your feet. Fortunately, it's slow enough that we don't get earthquakes. But that's and that's what is also happening on the moon, and that's really the connection. That's where tidal friction comes from, because as the tides raised on the moon by the Earth shift the moon's surface by a small amount, basically that's causing a loss of energy. That's what's stripping the energy from the Earth's rotation. That's why we need leap seconds, because the Earth is very gradually slowing down. It's about 1 millisecond, maybe a little bit more than that, per day per century. So it's a very slow effect. But if you don't do anything about it with atomic clocks, everything gets out of kilter. And before you know where you are, you're celebrating equinoxes and solstices in completely the wrong times of year. So that's the Earth slowdown, and it's actually the same effect, the same phenomenon that is giving rise to this gradual drift of the moon away from the Earth's surface. And actually, those reflectors that you mentioned, Graham, they are what are called corner cube reflectors, and I think the first 3 missions, maybe more than that, placed them on the lunar surface. It wasn't just one of the Apollo missions. These are banks of reflectors, a lot like the old cat's eyes that we used to have in the middle of the road. And what they do is send beams of light exactly back from the direction in which they came. So they've got a 180-degree reversal of the direction, and that means if you shine a laser towards them, you get your laser beam coming back. And modern technology lets you time the flight of the laser beam, which is why we know the distance to the moon with an accuracy of about 1 centimetre. It's extraordinary, totally extraordinary.
It is.
And that's how we know that I think it's 3.54 centimetres per year is the drift away from the Earth by the moon, which all leads to eventually the two stabilising. The end product of all this is that the moon will wind up about 500,000 kilometres away from the Earth rather than its 380,000 kilometres that it is now, and the two worlds will always face one another. Just as the moon faces the Earth with the same face all the time, the same will be true of the Earth. This is in maybe 10, maybe 20, maybe 40 billion years. It's a long way away. And actually other things will happen before that, but that's never mind. There was one other thing.
I've set an alarm on my watch.
Very good. Well, you might want to do one for the collision of the Andromeda Galaxy with ours, and the sun turning into a red giant.
Already covered.
Already covered. Good. Okay. So yes, that proves the moon. We know the moon's drifting away, and exactly as you said, in the age of the dinosaurs, it was a bit bigger. That's 66 million years ago. So the final. Let me just digress for a minute to explain why the moon is moving away by the same process, and what happens is that it comes about because the Earth's rotation is in the same direction as the moon's orbit, and these things everything's going anti-clockwise from above the North Pole, seen from above the North Pole. So the Earth's rotating, and that carries what we call the tidal bulge around with it, and that's the bulge in the oceans and the crust of the Earth. That's caused by the moon's gravity. So that's slightly offset from the direction of the moon. And what that does is it gives the moon itself a slight gravitational tug, which increases its velocity slightly. If you increase the velocity of the spacecraft, what happens is you move away from the object you're in orbit around. And that's why the moon's shifting.
Okay.
The final bit is, yes, that we do believe that the fact that the moon is there is one of the things that stabilise the Earth's rotation, and that will continue, I think, even when the two reach their equilibrium point in all these billions of years where each is facing the other. The moon will still be there. It's not going to vanish altogether. It will not be big enough to cause total eclipses of the sun, however. It will be significantly smaller in the sky than it appears now, which is a rather curious phenomenon, the fact that...
Yes, it's just coincidental that we can observe at this point in time. Yeah. It's a lovely effect too, and we get to witness it here in 2028.
Yes.
There's going to be a full eclipse, which will see a shadow run right across from the northwest of New South Wales, straight over us, where I am now, total blackout, and Sydney will get blacked out as well in 2028. Graham, thanks for your question. Great one. And you are listening to episode 250 of the Space Nuts podcast.
Space Nuts.
You've been listening to the Space Nuts podcast.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.